be like, I know last semester you had, the last part was kind of more conceptual, you didn't have as much math.
I don't know what I'm going to do for the test. I don't recall it being so conceptual last time, but
Well, I mean, like for the last part that we didn't test or we didn't quiz or do master sets.
Ah.
So are you gonna do something similar here?
not necessarily.
Oh,
I'll have a better idea as we get in a couple weeks. May 1st, I'll have a good idea. You want it sooner? Okay. And again, I try not to write my test too far in advance on purpose. Just in case the student says, hey, could you give me a sample problem on such and such? And then the only things that pop in my head are test problems. That seems like then I'm teaching to the test. So either you score really well because I just did a problem like that, or you don't get it and I feel defeated. So it's a lose-lose situation. Okay, I guess it's a win for you, but it feels like a loss. All right, other questions? Now that we're recording. I think the last time we did time dilation. And I think that's as far as we got. Is that the last thing?
Yeah, that was all.
Okay. So let's talk about the famous Hall and Rossi experiment of 1940. And it's probably just as well that they did it in 1940, because the year later, I guess at the end of the next year, we were at war. So the Rossi-Hall experiment, 1940. Hall, Rossi, Rossi, Hall. It's one or the other, typically. Oh, actually I have the paper here. Rossi comes first, okay. So, they decide to run a detector. And I always picture it being a bubble chamber. I probably should find out for sure. The bubble chamber was being invented about this time. So basically you take a chamber, a glass chamber, like an aquarium with a glass top, and you fill it with a superheated fluid. Now, superheated fluid is a fluid that is still gaseous state, but if you disturb it just slightly, it will bubble. And so you can basically boil it with a single charge. And what happens is, as a particle goes through it, then you get these bubbles. And if the bubbles look like that, the particle went in that direction because this bubble was created first, and it's a bigger bubble as it expands. So from this, you can start to look at particular particles. And they ran, just so we get the right numbers here, they basically set this up and they counted the number of muons going through it. Now you can identify sort of you can narrow it down. If I expose this to a magnetic field, as the particle is going through it, it will curve. And based upon the radius of curvature, you can figure out what the particle is, or at least narrow it down greatly. So just very quickly, if I expose the charge to a magnetic field, I get QVD is basically the force on it. Officially, QV cross B is the force on a moving charge going through a magnetic field. As it curves, that's going to be equal to mv squared over r. V cancels out. And what we end up with is the radius of curvature. No, that's not what I want. The charge divided by the mass is going to be the speed of the particle over BR. And so early on in identifying particles, you could do this and Also, which way it curves, you can figure out if it's positive or negative. The speed, you can figure out by the size of the bubbles. Magnetic field, you're setting R, you just measure. And so you can figure out what a muon is. Muon is a subatomic. It's, let's see, I've got stats around here somewhere. It's a spin half particle like an electron is. Its mass is 1.88 times 10 to the negative 28 kilograms. An electron, just to give you some idea, but that's mass. Mass of an electron, 1.99 times 10 to the negative 31st kilograms. Just to give you some sense of size. I lied about that, not 1.99, I got dyslexic there. 9.11. Now, I wrote U with a positive sign over there. That is just generic. Generically, you're going to assume a positive muon. However, it could be a negative muon as well. The difference in the mass between a positive and negative is negligible as far as we're concerned. So they took this chamber and they went up to Echo Lake in Colorado. Elevation of Echo Lake, 3,240 meters. They also set this up in Denver, Colorado. Elevation, well, it's about a mile, but 16 meters. Now, they're not claiming that the muon that they saw up in Echo Lake is the same one they're seeing in Denver, but we're basically getting bombarded by muons coming, well, in essence, from the sun. These particles come in, they will decay into various things. And so we're at the same time of day, the same position, we're getting bombarded by roughly the same number of muons. And so they figured you'd come up with an average of muons per hour here, average here, and you have a good sense of how many would have survived, how many of these would have survived when they got down to this level. Someone, I'm assuming a grad student, spent time calculating this stuff, or counting this stuff, and they came up with, whichever one I want to go with here, let's start out with, up at Echo Lake, 403.2 muons per hour. And the question is, how many are predicted that will make it down to Denver? Well, we have one other piece of information. We have the half-life. The half-life of a muon, well, we could go one of two ways, but let's just go with the half-life of a muon. 1.56 microseconds. So if I had a bucket of 100 muons sitting here in front of me, then after 1.5 microseconds, half of them would have decayed. In another 1.56 seconds, half of those would have decayed, so now down to a quarter. Another 1.56 seconds, another quarter, another half of that would have decayed, so now I'm down to an eighth of what I started with. So, as the muons are traveling this distance from Echo Lake, from the height of Echo Lake to the height of Denver, how many half-lives is that? Well, first off, let's figure out what that difference is. What is, let's see, so that's 24, 16, 24, I think. Now, how fast they're traveling, they did those calculations also. They came out with a speed of, on average, the speed of these muons as they're going through the chamber, 0.997528. 997,528, okay. So that's how fast they're going. I wrote beta equals, what is beta?
Velocity over speed of light.
Yeah, so that's V over C. So we can figure out how fast they're going in meters per second just by multiplying both sides by the speed of light. So 0.99758 times 3 times 10 to the 8. Probably good enough. Meters per second. And what do we get as the speed?
2.99 times 10 to 8. 2.991 times 10 to the 8.
Times 10 to the 8 meters per second. So it's going to be traveling 1,625 or 24 meters at that speed. How do we figure out how much time has passed? Given that speed and that distance,
Divide the distance over the velocity.
all right, so distance over speed.
Or yeah.
So 1624 divided by 2.991 times 10 to the 8th. It's meters per second.
So 5.428 times 10 to the negative 6.
5.428 microseconds. You said times 10 to the negative 6th? Okay. So that's a lifetimes that passed. We can figure out what the prediction would be at the bottom. I have certain number of particles would exist given the initial value times 1/2 raised to the t over the half-life. Since we lose half every time the half-life passes, so this would be, we start out with 403.2 times 1/2 of 5.428 microseconds over 1.56. Looks like they have a lot of faith in you, Patrick.
What's that top number again?
That's 5.428. That was the time in microseconds that at that speed would pass.
I got 36.149.
All right, so that is the prediction. If there's no relativity at all, if this is just straight Galilean relativity is all that's valid, then would be the number of particles on average per hour that would be showing up in Denver. Now, if we do relativity and it turns out to be 37, there's really no way to tell the difference between the two. But fortunately, relativity gives us a very distinct, very different answer. All right, sorry. No, I'll go to a new screen here. Or not. Oh, there. Okay. Now, if relativity is in effect, that time right there, the 1624, that was the distance from the scientist's point of view. That's the speed the particle is going from the scientist's point of view. And that's how long it would take from the scientist's point of view. But what about from the muon's point of view? If time dilation is valid, then I know that t is equal to gamma times the proper time. So this would be the time from the muon's point of view. Gamma is 1 over the square root of 1 minus beta squared, which is 1 over the square root of 1 minus 0.99758 squared. And while that's getting calculated, so the proper time would be t over gamma, which is the number that you're about to come up with there, 5.428 microseconds divided by
14.231.
Same.
All right, for 14.231. And just a quick check here. Gamma should be big, the smallest gamma can be is 1, unless we get into imaginary numbers, which is a different problem. So I'd expect gamma to be something bigger than 1, which it is. The closer it gets to this, the closer beta gets to 1, the closer the gamma gets to, I guess, infinity. But what do we get is the proper time?
Zero point 381.
0.381,
Yeah.
and that would be microseconds. All right, so relativity is predicting that from the muon's point of view, only 0.381 microseconds passes. So the number of particles then predicted would be, same formula as we had before. So 403.2 was the initial amount, times 1/2 of 0.381 over 1.56.
$351.162.
351.162?
Yep.
All right, so we have two very clear, distinct predictions. The other prediction was 36, this one is 351. The actual number that they found was 339. Pretty darn close to the prediction based on relativity. Very much not close to the value predicted if relativity was not ended. If relativity were bunk, we would have gotten a very different answer there. So 1940 is the first clear evidence that special relativity is true. The experiment was repeated in 1963, let's see, that is the Frisch-Hall experiment, or Frisch-Smith, 63. They pretty much did the same thing, came out with similar evidence. The next big evidence came in 1972, early 70s, where they took an atomic clock, had them synchronized down to nanoseconds, put one onto a plane that flew around the world, and then they got back and they compared the two differences. And there was indeed differences in the atomic clocks as they started to get noticed that, because obviously planes traveling faster than the ground is. So at this point, I don't know if it's pretty much assumed to be true, and any experiments being done are just fine tuning the ones that have already been done. Questions to there?
How do you apply this?
Well, my dissertation. In terms of your everyday life, satellites for GPS are moving at several thousand miles per hour, or several thousand meters per second also. Several thousand meters per second, and over time the timing starts to get off, and I think it's 30 meters a day. It would be off by 30 meters a day if you do not take special and general relativity into account. So that's probably the most direct impact upon everyday people.
trouble with the satellites, though, in terms of doing the calculations, is most calculators can't handle it, so you have to at some point do approximations, but they're still in effect, even though from a practical point of view, it doesn't seem like much, but it is enough just to keep throwing it off every day. It eventually would be right again. Other questions? Was that sufficient?
Yeah.
Okay. Other questions? Okay. So, we got these two different points of view, obviously different times. Do they agree on anything? They're definitely not agreeing on the amount of time it takes to get from the 3240 meters to 1616 meters. They agree on two things, these 2 points of view. I'm giving Yuan sentience for the sake of this. They both agree the speed of light is roughly 3 times 10 to the 8th meters per second. They both agree upon the speed. They just disagree what's going at that speed. From the scientist's point of view, you have Echo Lake and Denver, and the muons are traveling at point beta is 0.997528. What do the muons see? What is traveling that fast?
Everything else.
Yeah, pretty much. So from the muon's point of view, so this is what we'll call the lab frame. And the muon frame, you have Denver here zipping towards it and Echo Lake zipping away from it at that speed. Now from the muon's point of view, Denver is zipping towards it at 0.997528. So how far does Denver